Hello everybody, today in calculus we're going to do a quick tutorial or more of like a patch on the following topics right here, talking about domains, continuity, and also differentiability. And just to kind of keep your attention, there's my son on the right hand side. You can see that he is sleeping and his face is pretty big. So here it is. The first part I want to talk about is domain versus continuity. Does one imply the other? Meaning that if you have a function over a certain domain, does it mean that it is continuous over that certain domain? Well, the best example that I can give you is the following then. Let's say that we have y is equal to the square root of x. Now, the graph of it, you can see it looks something like this, and we can say that the domain is going to be for x that is greater than or equal to 0. But in terms of continuity, well, that's a little bit different because continuity it is actually not continuous at x equals 0. The reason for that is there's no limit on the left-hand side. Remember, continuity is defined by having a limit coming from the left, which is agreeing with the limit from coming from the right, and then therefore the limit exists. Since there's no graph on the left-hand side, then therefore there's no limit then. So in terms of continuity, we can say that that's only for x that is just strictly greater than 0. So does that mean that if you have a domain over a certain interval that is continuous? The answer is no. The best way you can define it is that if your domain is going to be from A to B inclusive, it doesn't necessarily mean that it is continuous from A to B for that small little bracket. Because maybe we can also have something like, say, a jump continuity in this case, where you can see where every word is defined within A to B, but it is not continuous then at that point. But if it is continuous from A to B, that does imply that domain is going to be from A to B then, because in order to draw something that's continuous, you have to be able to draw it so that without having to lift your pencil then. Okay. Next, now let's go ahead and talk about continuity and differentiability. Meaning, if it's continuous, then is it differentiable? Well, another counterexample in this case that I can give you for this one would be maybe like, say, the function y is equal to the absolute value of x, or in this case, maybe something like absolute value of x minus 2. Notice that it is continuous everywhere, but the problem is that it is not differentiable at x equals to 2 because, again, differentiability deals with the concept of limit. The limit, while it exists at x equals to 2, coming from the left and coming from the right, but by definition, when you set up the slope, right, trying to find the slope coming from the left, that's not the same as the slope coming from the right. So as a conclusion, because your differentiability is defined by using limits, then therefore it is not differentiable there. So just like before, what that means is that if you have a function where it is differentiable from A to B, then yes, it is considered continuous on A to B, but it's not the other way around. If it is continuous on A to B, that doesn't necessarily imply that it's differentiable from A to B. Now, let's go ahead and put the very beginning and also the very end together. If you have a certain domain, does that mean that it's differentiable everywhere? And obviously the answer will then be no then, because if we connect the two together, here you can see maybe a graph of that then. So let's say that we have a domain that is all real numbers, and the graph might look something like this. So here you have like kind of like a curve, you have a closed circle, and then here you have like an open circle that continues on the bottom. But now you can see that because it is not continuous at x equals 0, then therefore it is not differentiable. Maybe the slope from the left is the same as the slope from the right, but unfortunately, because there's no continuity, that means it doesn't work then. So conclusion in this case is that if it is differentiable on A to B, the interval, without the endpoints, then it is going to be the case where the domain of the original function is from A to B, inclusive of the endpoint. But if you have a function with a certain domain of A to B, that doesn't necessarily mean that it is differentiable from A to B then. And I could change this into actually a, what is it called? Exclusive of the endpoints. Okay, so now let's go ahead and look at an example of a problem with all of these connected together. What I'd like to do is solve for A and B so that f is differentiable everywhere. So f is going to be defined by this piecewise function that we have below. Now, what that means is that there are two conditions that I need to look at. First of all, it is continuous at x equals to 4 because that's where the break is going to be. And then if it's differentiable at x equals to 4, then that means the slope from the left has to be the same as the slope from the right. So here is kind of like my two setup then. So for the continuity part, I am going to go ahead and say that the equation on the left, limit as x approaches towards 4 from the left of f of x, has to be then the same as the limit as x approaches 4 from the right of f of x, which is equal to f of 4. Well, that's really just kind of like saying plug in 4 in both equation and see what happens if they come out to be the same. So plugging in 4 into the first equation, we get 1/2 multiplied by 16 plus 1. And that is supposedly equal to plugging in 4 into the other equation, a multiplied by 2 plus b. And that's the same thing as f of 4. So we can just go ahead and not write the right-hand side. But what we have right now is that we have 8 plus 1, so that's equal to 9, is equal to 2a plus b. And if you can kind of get the feeling for it right now, what's going to happen is we have two variables that we need to solve for a and b, so that means we need to come up with two equations and two unknowns. Well, that's where the next part comes in. Now we're going to look at the differentiability, right? So we have to make sure that it's differentiable at x equals to 4. So what that means is the limit as x approaches towards 4 from the left of f prime of x should be equal to the limit as x approaches towards 4 from the right of f prime of x, meaning that their derivatives have to be the same from the left as it is to the right. So solve for the derivative of each one of these. The first one, f prime, is going to be equal to just plain old x. Whereas this guy right here, f prime, for x that is greater than or equal to 4, that is going to be equal to a divided by 2 root x. So now I'm going to go ahead and set them equal to each other at the value of x is equal to 4 because I want to know what happens at that point then. So on the left-hand side, we are going to go ahead and plug it into this guy over here. So from the left, you get 4. And on the right, if you plug 4 into here, then you're going to get a divided by 2 multiplied by the square root of 4. And if we clean that up a little bit, then we get 4 is equal to a divided by 4. So it looks like a is going to be equal to 16. And if a is equal to 16, we can easily plug that into here to solve for what b is equal to. So 9 is equal to 32 plus b, so it looks like b is equal to negative 25 then. So there you go. That's going to be our system of equation. So in conclusion, what I'm trying to get to you to understand is that when they say that the function is differentiable, you can conclude that it is continuous over the domain that it is preserved for. So that is to say, if you have a function and it is differentiable, then the derivative should also be it should be a function where the domain is going to be defined as the original function then. Okay, and that's it. All right, thank you so much. I'll talk to you next time.